questions with 15 H index, 31 I-10 index, and 1200 plus citations to his credit. We welcome you, Dr. Adarsh, and request you to start the session.
Many thanks, Dr. Shikha ma'am, for introducing me in this sessions, and many thanks to you and Dr. Mukta for inviting me, for organizing this event and inviting me to deliver a talk. Let me start with my contents. So I'll be covering the quantum computing technologies and algorithms. So before I start the presentation, I have one request to the organizer. Like here from the last few days, it is raining heavily. So in case I get disconnected, give me a phone call. I'll try to make an alternative arrangements.
Sure,
so coming to the contents. I'm having a background in computer science. I do not have a background in physics. So I'll be covering this session from the computer science background. So I'll be mainly covering the software which is being used for quantum computing and quantum programming. So I'll be introducing, I've seen your videos. There were earlier speakers who have covered the QCA basics. So I'll be covering the algorithm implementations in QCA and then Silk. So if I'll give an overview of what I'm going to cover today, earlier speakers have covered the quantum gates and quantum circuits. So I'll not take much of your time to cover these contents again, since I need these content to be covered in the quantum algorithm. So I'll give a quick overview of this. Within 5 minutes, I'll introduce you with the quantum computing, quantum gates and circuits, what are tensor products, and what are the other concepts which are associated with the quantum gates and circuits. And then for next 1 hour, my focus will be on QCA programming, how to implement the algorithm. So the basic purpose behind this QCA programming is to show you why the quantum computation is better than classical computation. So we need to take examples. So we have studied using theoretical analysis and using mathematical equations that quantum computing is better than classical computers. But if in terms of implementation, how you can justify that it is actually working in a real environment. So we'll be covering a few of the algorithms, like Bernstein-Vazirani algorithm is the first algorithms we're going to take here. What is this algorithm? Like if somebody is given a challenge to guess a random number, like I'm the challenge provider and somebody is solving the challenge. I have randomly picked a random number and asked random challengers to identify the random number. So there could be n constraint. For example, if it is a 2-bit number, the challenger has to try 90 possible combinations to identify the right number. So now length of the random number could vary, right? So then the complexity of the searching will vary with the length of the random number. So in a traditional classical algorithm, we require large number of combinations and then matching. Whereas quantum computing claim that this can be done in one shot. One shot means in one go we can identify what is a random number. It's possible in a quantum computers, so that's why the quantum computation is better than the classical computer. So Bernstein-Vazirani algorithm, we're going to see what is this algorithm. We're going to take an example. We're going to implement in a classical computer, and then we're going to see in a quantum computer. Then is the Dutch algorithms. So Dutch algorithms is another algorithm. This is the first algorithm which proved that quantum computation is better than the classical computations. So if you talk about the Dutch algorithm, what it say is you can have 2 type of outputs. One is the constant output, and the second one is the random output. So when does a circuit become a constant? When does it become the random one? Right, so that we need to identify. So if you are flipping some coin, so the possibility that you will get 0 and so we need to check the input and output. So if we are flipping 2 coins, there could be 0, 0, there could be 0, 1, 1, 0. The different possible combinations are there. So if both are matching, if both of the coins output is matching, we can say it's a constant one, other one is not a constant one. So how will it solve this problem in quantum computers? So can quantum computer identify in one go rather than two go? So in a tossing a coin twice or two coins once, we need two set of experimentation. And is it possible to identify whether it's a constant output or a non-constant output with one go? So that we need to identify with the quantum computation. And then is a Grover classical search algorithm is there. Like we have in our data structure, we have a large number of searching algorithms which take n comparison to identify a right number or n by 2. So whereas the Grover algorithm says that we can identify a person, we can identify a number in a list with maximum square root of n. So there, the computation in Grover's algorithm is faster on quantum computation. So we're going to see how the Grover algorithm work in a classical scenario, and then we'll see how it work in a Qiskit. And then is we'll be going to take a real-time problems. So so far we have seen that like how you can use search over the quantum computations. But what about the real-time problem? Let's suppose you are planning to invite your friends for a dinner party, right? So there are different friends from different regions, and there might be some issues within the friends. So somebody is not comfortable with other person. So you have to make a right combinations, like to whom to call and at what time to call, and then your goal should be like maximum people should come to the party, right? So can we solve these problems with quantum computation? So we're going to take this problem and we'll see what are the probabilities in Qiskit, what are the probabilities that we'll be getting the maximum people, and what are the possible combinations. And then one of the important algorithm is the Shor algorithm, and the topics like quantum Fourier transformation, quantum phase estimation, and the comparison of these is lying in the Shor algorithms. Now, I mean, for a computer engineer, the importance of Shor algorithm mainly lies in the cryptographic world. If you consider the cryptographic algorithms like RSA algorithm or elliptical or Algorithms algorithms or Diffie-Hellman algorithms, all of these algorithms picks random numbers. So picks a random number, do the multiplication. For example, if you're considering the RSA algorithm, it calculate phi n. So phi n is a minus 1 into b minus 1. So a and b are the random numbers, right? So we're picking the random numbers and doing the multiplication and doing generating some number. And from a technical point of view, can we reverse the process? We have a random number. Can we identify exactly what were the prime factors of a random of a number? So Shor algorithm help us to find this in a quick fashion. So that's why it's being said that with the possibility of implementation of this algorithm on a quantum computer, we'll be able to break most of the cryptographic primitives and protocols, right? So you can imagine the quantum internet security, which is using the traditional approaches of encryption, decryption. If this algorithm will be successful, then the quantum internet security will be on stake. The internet security will be on stake. And Qiskit is one toolkit. In first few slides, I'm going to show you what are the possibilities, what are the other possibilities. There are large number of possibilities are there where we can do the computation, quantum computation practices. And the second toolkit, which is important, which is Drive in 2020, is the Silk one. So in a Qiskit, you are getting a token, and you can implement a limited number of circuits, right? So, and you need to identify which system is available. So you can identify which, there are different quantum computers available by provided by IBM at different locations. So we need to identify which system is more occupied. Is our circuit execution differ from location to location? So that we need to identify. So I will give you a picture of it, how we can do that. And then if you want to practice on your own computers using Eclipse or other IDEs and integrate the Silk libraries, and once you have everything tested and verified, then you integrate your final circuit on Qiskit and do the implementation of quantum computer provided by IBM, that would give you a clear picture, because Silk provide you unlimited access. So we're going to see a few programs, how the Silk is helpful in this. And then is the software practices. So recently, many of the computer science concept, the software life cycle, for example, is associated with the software one. So what are the software fields which are integrated with quantum computing, how we can take the advantages, like annealing is there, quantum annealing is there. So quantum annealing is, mainly used for optimization and the sampling one. So which is largely used in the AI/ML approach. So we can do the classifications. If you have, you want to do classification of two categories, then how you can implement in quantum computations. What are the software practices with? Yes, ma'am. Yes, ma'am.
Sir,
Am I audible?
yeah, you are audible. We are on first slide right now on the presentation outline itself.
Yes, ma'am. It's on presentation outline. I was giving quick overview.
Okay,
It's moving to next
okay.
slide. So these are the important references. Few of them are my publication and books, and other are from the other authors. So these are, the content which I'm going to cover is mainly from these published material. So, right. So see, you already know the difference in a quantum and classical computers. So in quantum, we represent the bits into quantum qubits or quantum bits. We represent Bra and cut notations. So cut 0, cut 1, or the Fourier transformation. Cut plus, cut minus, and like that one. So the issue with the quantum computer is there is need of large power, and we use the quantum annealing concept to identify the energy efficient solution in quantum computation. Whereas in case of classical computation, the power is varying linearly. So, and then quantum computers is having a high error rate. So many post-quantum cryptographic approaches suggest to integrate the quantum error approaches, error correcting codes. And then like there are optimization and data analysis approaches where quantum computing is doing much better, because we have just discussed that there are algorithms like Dutch algorithm is there, Grover algorithm, Shor algorithms, which give a faster computation. So how those will be useful in efficient data analysis and within a limited time, a stimulated time. So you all know that quantum technology, quantum domains is nowadays very wide domains, but from a software perspective, so these are the areas where I found interest. So there are large number of areas like quantum cryptographic, quantum primitives and protocols, cryptographic primitives protocols, which include quantum key distributions. So like I was looking at your one of the videos. The person has covered BB88 algorithm, so E89, E92. There are various quantum key distribution algorithms are there, through which you can understand how the keys are distributed. And then quantum software and the quantum clouds approaches are there. So we're going to see what is a software, quantum software life cycle. There it will be giving more pictures, since it is expected that the quantum computer will break the classical cryptographic approaches. So there are post-quantum cryptographic approaches as well, like post-quantum encryption, decryption based approaches are there. So likewise, in various domains, we can integrate the quantum technology. So I don't want to take much time on this topic. So you know the circuits. So a buffer circuit, NOT circuit, NAND circuit, AND circuit. So these are the classical circuits. The various circuits are there in the classical computers. So likewise, there are circuits available in the quantum domains as well. So this is the one picture of the circuit. So you just have to note down what are the symbol notations, and there is use of a matrix for each of the circuit. And like we can go internal to the circuits, how matrix is generated from the circuit, or how circuit is generated with the matrix. So we can do both way. If we have a circuit, we can design a matrix. If we have a matrix, we can design the circuit. We can give some input, output, and observe our outcomes. So this is the one out of these gates. What I'm going to use most I mean, at large today is the Hadamard gate. So Hadamard is very popular gate in most of the algorithms, whether it's a Dutch algorithms or it's a global algorithm, Shor algorithm is largely used. And one property of Hadamard gates is you apply Hadamard gate twice, it gives you an identification gate. So what is this property? You might have learned this property. So how to use this property in our algorithms, that we are going to see today. So, I mean, since Hadamard is a popular gate, so I give you a quick overview how does Hadamard gate look like. So if you see from the metric perspective, it will give a superposition state. So it represented 1 by square root 111 minus 1. So you can represent 0 bit as 1 by square root 0 plus cut 0 plus cut 1. And likewise, you can represent 1 as 1 by square root cut 0 minus cut 1. So there are two states, two qubit state, cut 0, cut 1, we can represent, right? So this is the, I mean, there are two type of bases. This is the computational base. If you write cut 0, cut 1, that's a computational phase. And likewise, there is a Fourier base also. So cut plus, cut minus are the Fourier bases. So if I try to represent a plus cut, into Fourier base, it will be same as 1 by square root 2 cut 0 plus cut 1, right? And likewise, if I represent minus cut, it will be like 1 by square root 2 0 minus cut 0 minus cut 1. So we can represent Hadamard gate in both of the bases, either in computational basis or in the Fourier basis. So we are going to see this with an example when there is a need of this concept in the algorithms. So I will briefly introduce you. So there's an important property like H square is equal to ID. This we need to remember because Hadamard is widely used gate in almost every circuit. When you are designing a circuit, you should know you're expecting some kind of output. And in there is in the quantum circuit, there is a black box circuit. I mean, you know what output you want, but how to get output is not known. So how to do that? You start practicing with the Hadamard gate because it gives a superposition state. So with the superposition, the 50% probability of getting both of the bits, and later we can integrate various other circuits, what output we want. So we'll take this with an example. Right? So in Hadamard, you can apply Hadamard in a serial fashion or in a parallel fashion. Mostly we apply Hadamard in a parallel fashion. Like you can see, if there are multiple Hadamard gates are there, and you can apply in a parallel approach and giving cut 0 in almost every input, you will be getting cut 0 plus cut 1 by square root 2. So every output will be giving this. And if you have to consolidate this, if you put measurement and put the measurement over a classical channel, then you need to do the tensor product. Now, what is a tensor product? You might have learned, and you might be knowing this, but we will be understanding with an example of this as well. So mathematically, there are ways to represent this. I'm not going into this mathematical derivations right now. So my more focus will be on the implementation perspective, but in few cases, I'll be going in detail where it is required. So you can combine qubits in a multiple way. Like I told you, you can combine a serial way or in a parallel way where you need to do the tensor product. So this is just giving you one example. If they're single qubit, how it is represented. If there are multiple qubits, how you can combine it. So X and Y, two qubits are there, the multiplication will give the result to 0, 0, 0, 1, 1, 0, and 1, 0. So you can keep two X at one point, like cut 0 plus cut 1 by square root into cut 0 plus cut 1 by square root on other side. You can do the multiplication. We'll understand with an example of this also. I mean, this is more derivation, how this multiplication is being done. If having some magnitude, magnitude is also multiplied, right? Amplitude, sorry. So if you're doing a tensor products, so like we did in a previous slide, so what is result to? So tensor product give us a bigger space. If your smaller qubits are there and they're lying in some spaces, so multiply two bases, they give us a bigger space. Obviously, they will give a bigger space. Like we have two single qubits which are multiplied, and then it will result to 2 qubits, and with 2 qubits there are more possibilities. So the space of the result of the tensor product will be large, right? So what we need to understand, like before to understand the algorithms, So how does the Bernstein algorithm work? How does the Dutch algorithm work? We need to understand if we're putting some gate in parallel or in sequence, what it result to? And we have constantly measured the output. If we keep on doing like this, we'll be getting the success. We'll be getting what we want, right? So if you're putting some header mode gate in parallel, I told you if you're putting header mode gate in serial, it gives you an identification. So if you're putting in parallel, it has to give output in a superposition state in each for each of the inputs. So for parallel, you need to do tensor product as well. So we need to see this with the implementation. And in general, in a mathematical form, it is represent this way. How this mathematically is being derived, I'm not going right now into details. So like a header mode gate, another important gate is control node gate. So this is also widely used in Dutch algorithms because we can combine 2 or more gate as well. We can combine Z gate with NOT gate and it become control Z NOT gate. And 0, 0, I mean, if you just see the plain control NOT gate, it is, this is our output. If you're giving input as 0, 0, output will be 0, 0. And if you're giving input as 0, 1, output will be 0, 1. Input 1, 0, output will be 1, 1. This can be better understood with this circuit notations. So you can consider first bit as A and second bit as B. So if you're giving 0, 0 and input, so output on the first channel, first quantum channel will be 0 only. So there is no operation we are applying. We are applying XOR operation from A and from the B. So let me see. From there, the input is coming directly. From here, we are applying the XOR thing. So when we're XORing, then it is resulting us to something. So if you're passing 0, 0 here, you're passing 0, 0, so A will be 0 only, and 0 XOR 0 is 0, right? So then we are passing 0, 1. 0, 1 is here, 0 will be here, and 0, 1, XOR of 0, 1 is 1. So that's why the output of this is 0, 1. Now it is 1, 0. If you are applying 1, 0 here, so this output will be exactly 1 because passing directly, and then there will be XOR of 1 coming from this side and then 0 from this side. So XOR of 1, 0 is 1. So that's why output of 1, 0 is 1, 1. So likewise, you can do computation for 1, 1 and you will be getting a result of 1, 0. Right, so you can derive this from the matrix also. So there is a matrix. I told you there is a circuit, there is a matrix, and we can derive a matrix from the circuit and circuit from the matrix as well. So how does 0, 0? If there is two qubit representation is there, 0, 0, it is represented in matrix form. It will be having 4 rows and 1 column, right? So and if overall circuit will be having this matrix. You can do multiplication of the bits with the circuit and get the final output. Or I mean, I have just explained you how to use the circuit to get the output. You can use the matrix also. So I'm not right now going how to do the matrix multiplication. This normal operation you can understand yourself. And then you can apply header mode gate with control node gates. So this is also widely used in Dutch algorithms. So it's important to understand how to apply header mode with control node gate. We can do this. So this is a more detail of it, how it is applied. Like I explained you by passing 0, 1, 1, 0. Likewise, you can do computation here as well, and you will be getting the results. So I'm not explaining this one. So in addition to this, header mode gate and control node gate, there are other poly gates also. The X gate is popularly used in most of the algorithms. So we're going to use the X gate. Yeah. So in addition to this, I told you we can combine multiple things. So in Qiskit, you might have seen a Q sphere. In a Q sphere, if you're using the computational basis, mainly the vector lies on 0, pi by 2, or 3 pi by 2. But if you want to give us some phase input at some 45 degree, 30 degree, then you can integrate the phase qubit or phase gate as well. So what is a phase gate? How you can apply the phase gate? What it result to? We'll see use of it in our third algorithm, right? So in quantum, if you are applying multiple gates, so multiple gates you're applying on a quantum channel, or you can combine and put into a one box, which is called as a quantum circuit, right? So, and there is a one important concept in quantum computation, which is called as a black box. So in software engineering, we have learned what is a black box. We're just knowing the input and output. So we're passing some input, we're getting some output. So if you are a developer, your role will be to design a quantum circuit to solve some problems, and the other party will not be knowing what computation is being done inside. So they will be only knowing that what is input, what is output, are we getting the desired output or not. So likewise, there is use of black box circuits, like there is an oracle circuit and the reflection circuit using Shor algorithm. So what is oracle circuit? What is reflection circuit? Like, we can have negative inputs, and to handle the negative input, we need to design the circuit. So this we can do using oracle circuits. And for the reflection one, we can apply the phase gates. So phase will be shifting from one position to other position with the target that we need to reach our goal. And goal could be anything, like in Grover algorithm, we need to search our target in an efficient way. So whether with the movement of the vector, we are moving close to the target. So that would be the role of a reflection circuit. So give a picture where the vector and where is the reflection. Is it moving close to the winning target or not? So that we'll see when we'll discuss the Grover algorithm. Right, so we can combine this in various ways. We can apply Hadamard gate, control net, and then Hadamard case. Just giving in a picture what we can do. We can do a lot more of things like this. So there is another U gate is there. We can have a single qubit circuits or multiple qubit circuits. Both are possible. So multiple qubit circuit will be having multiple inputs. Like just now we have seen multiple channels. So each of the channel will be providing a single qubit and will be getting the output. So we can do some sort of multiplication here in this domain also. There are few examples here as well. So how you can represent in a linear form or in a vector form, any qubit in a linear form or a quantum vector form. And we can do various type of multiplication as well. So I'm not going right now, I'm not going much detail into it. So you can see one example here. So you can take some vector A and some vector B. It's having some different amplitude. Like A is having 1/2 cut 0 and square root of 3/2 cut 1, and B is having iota by square root of 5 cut 0 plus 2 by square root of 5 cut 1. And when you're doing the tensor product of this, you can see how you can do this. So this is this notation, how you write the tensor product. And then you are taking this one first, multiplying with this. So this is the thing. So then you are picking this one and multiplying with this. This is the result. And just pick this one and multiply with this right here. And then pick this and multiply with this and do here. Likewise, you can do normal mathematical computations. And in QCA, you might have seen that there are probabilities. Like what is the probability that 0, 0 will come? So this amplitude, the square root of the amplitude will give you what is the probability, right? So we'll take this example, but right now, like if I consider 0, 1, so what is the probability that 0 will come if I use these two qubits and do the tensor product, or design a circuit where these two inputs are used and there is a tensor product applied. So the probability will be 1/5. So square of 1 by square root of 5. The 1/5 will be the probability. So that probability we can draw. So that in Qiskit, there are two options. One is we can drag and drop the circuit and automatically the codes are generated and we can analyze the output. And the second is we can take the help of a Jupyter notebook. There we can call the Qiskit libraries and we can use the simulator or the quantum computer. We can specify the quantum computers and we can do the computation. We're going to see this with an example. Right now, you have just remember this, how does the probability is calculated? The square root of the amplitude will give us the probabilities. So the various other examples are there in this one. In some other time, I'll be explaining those things. Like this would be an interesting one. Like for example, if we are having two things and it's not represented in a linear form, is represented in a matrix form. V and W are there. You can do the matrix multiplication like this also. Let me explain you. Like this is the V1, this is the W1. So you can see what you are doing, what multiplication you are doing. So V00 is multiplied with, see this square box. So V00 is multiplied by every entity of W. And likewise, V10 is multiplied by every entity of W. So likewise, you are doing a lot of computation here. So you can understand the simple mathematics. So likewise, a lot of examples are there in this slide where you can understand how the computation is done. So like the single qubit gates, multiple qubit gates also. So these are the multiple qubit gates and their matrices. So this is also widely used. And they are, they are cut notation, bra and cut notations are there. You can do multiplication of bra with bra and cut with bra, and like that way you can do the computations. So this given one example how the matrix is generated from the a final matrix is generated from the qubits. So using the cut notation to the matrix. If you want to design, if you know the inputs and you want to design a final matrix, then you can use the cut multiplication notation. So like this is an example. So likewise, if you have any randomizer, not the predefined circuit, but any new circuit is there, and you're passing some input, you're getting some output, you have the output with you, and you can do multiplication of input and output, and then you can get the final matrix. And later on, there's no need to reapply those circuit. You can use the matrix as well for the computation. Right. So some of the mathematics to represent the same thing. Right. So and large number of circuits in a quantum domains are the reversible circuit, like control NOT gate is a reversible circuit. So and what is the reversible circuit? If for the input you are getting an output, like in left hand side 00 output is 00, 01 output is 01, right? So for input 10 output is 11, and if you're passing 11 output is 10. So input and output are lying in the same space. So whereas in case of non-reversible circuit, it is not possible, right? So let's come to the real picture, how we can use, how a computer background person can use these quantum computing concepts in Qiskit and other simulators. So there are various quantum programming languages are available. So what those languages is managing the physical devices. Nowadays, we have the quantum computers provided by IBM. We can take advantage of those quantum computers, and we can do our computation, solve our problems, and the predict quantum algorithm execution cost on possible devices. So what will be the execution cost? Like we're going to see, we design some circuit and we want to give some input and we want to observe some output. So if we are going with one shot with one execution, what is an output? Is it the desired output? And if we increase the number of shots, let's suppose to 1,000 or 1 million, so are we getting the same result? If yes, that's fair enough. We got our circuit verified. But if not, what is the probability that we are getting the desired output? So those kind of execution and their analysis is possible. So examine quantum computing concepts, solve the quantum computing concepts. We can understand how the qubit is varying on a quantum channel, how after measurement it result to a classical output. And we need to do the testing and verification of the quantum algorithm also. Like I told you in a Shor algorithm, we required oracle and reflection circuit. So there are various ways we can design the oracle circuit and the reflection circuit. It's not like fixed, I have designed one thing and that will be only solution. There are multiple solutions are there. If you go to the GitHub repository or the Qiskit help web page, you will be finding multiple solutions for the oracle and the reflection circuit. Likewise, multiple solutions for other are also available. So we'll have a quick look over it. And like there are many languages available. So if you want to execute instructions step by step, the imperative programming language like QCA, QSM, Silk is there. So Silk is recently being developed, and it is popularly used. I mean, it's giving giving a least constraint, at least no constraint on how many circuit you want. So, but execution will be on a your classical computer. It's like a simulator environment. So likewise, there are many other languages are available and tools are also available. So I have one article on quantum computation in Village. So you can search that articles. I told you in the first few slides also the important references. You'll find the complete reference of that article in that slide. And there I have done the comparative analysis of almost 50-60 toolkits and what programming language they use, what are the other features. So you can go to the articles and you can find out the details. So what are the challenges with right now? The challenges with quantum computing is right now is an error prone. So there are probability that you might not get the desired output. So there are need of error correction, error detection mechanisms. So we can integrate the traditional error correction detection approaches in this, and there are many hidden variables are there. The major approach is like if you are considering, if you want to integrate some, you want to implement some algorithm, and you're considering something as black box, but what to design, how to design. There's no standardized procedure to design a black box. You have to make your hit and trial. You have to observe the output. So that is a bit tedious task, but quantum QuizKit has made it much easier. And right now, the quantum computer is I mean, the available quantum computer is having less than 100 qubit, less than 100 qubit quantum computers are available. Like what I read is like 50-60 was available a few years ago. Right now, 80-84 is available, but it's less than 100. But less than 100 qubit quantum computer is available with us. And this need of open source SDK also, we can modify. I mean, large number of open SDKs being developed in the recent years, last year. So I've given the pictures. So I'll be mainly using the QuizKit in this sessions. And in QuizKit, there are many libraries are there. So it all depends what you want to do. So we'll be using the QASM. If you see the first column in the IBM sections, so there are large number of companies. First of all, the large number of companies which have developed the quantum things, quantum simulators, quantum programming languages. But today we're going to see the QuizKit and the Silk one. And if you see the QuizKit, we'll be using QASM simulator in the Jupyter notebook. We're calling QASM simulator in the backend. We do some kind of computations and to use the predefined circuit. Like sometimes we might not be successful in getting the exact circuit. So what we do is we take help of a GitHub and in QuizKit GitHub repository is available. So like for example, in today's class, we'll be discussing the Shor algorithms, but Shor algorithm circuit is a bit complicated. So what we're going to do is we can take help of QuizKit Aqua. So you can see the quantum algorithm QuizKit Aqua. Its deprecated version is available over the GitHub, and new version might be available, but you can download the deprecated version of this QuizKit Aqua, and you can use it. So I'll be teaching. I'll let you know how to use that one. So you have to design what you want to do, and the QuizKit obviously we're going to use drag and drop features we're going to use. In addition to this, there are large number of languages are available. So this is one classification, one picture of the quantum programming languages and the tools which we can use. So let's start with the QuizKit quantum programming. First, a quick overview. So you can go to the quantum QuizKit website. You can create a sign in. You can create your account, and after creating an account, you have 2-3 options. I mean, launch composer, launch lab, and recently they have added one more option also. But we have to go to the launch composer. So in launch composer, we have to go to quantum composer. Then we need to do what circuit you want to implement. For example, the X gate, poly X gate or NOT gate is having this matrix 0, 1, 1, 0. So and you're applying this gate over cut 1 and cut 0. So I told you you can do the computation using a circuit or using a matrix. So this is using a matrix. You have used X, which is 0, 1, 1, 0, and then is 1, cut 1. What is cut 1? In a single qubit, cut 1 is represented as 0, 1. So you can do the normal matrix multiplication, the result will be 1, 0. And what is 1, 0? It is nothing but cut 0 representation. Likewise, x cut 0 is there, and x cut 0 is, you have a matrix 0, 1, 1, 0, and it is multiplied with 1, 0 and result to 0, 1, and which is nothing but cut 1 notation will be there. So output will be cut 1. So this understanding of quantum, this one, quantum X gate. So same X gate you can drag and drop. So after logging and going to the composer, you'll be getting a quantum channel and a classical channel. So both channels, is required, and quantum will be varying the quantum bits. And over the classical bit, when after completing the quantum circuit, we apply the measurements. The measurements output will be evaluated on the classical channel. So we'll be getting over a classical. We need a classical channel for that. So you can drag and drop. So you can see on top of top bar there are different colors, and different colors are representing gates. So first is the header mud gate, a NOT gate,
So this is
control NOT
some
gate.
ID. Excuse me, sir.
This is the online one.
This is online and freely available.
Yes, you can create free account. You can use. This is available for public.
Okay. Quantumcomputing.ibm.com, right, sir?
So you can go to the website. It's mentioned on top.
Okay. Okay.
Right, so there are multiple quantum circuits are available. So this is a drag and drop. Those who are beginner in this domain, it will be easy for them to start practicing with the drag and drop feature. You can drag those gates, and you can observe the output. So I'm going to take few examples. Like we have dragged two XOR gates, X gate. And if you see on right hand side, it's generating automated codes. We can vary the codes, and the circuit will be automatically changed, and we can observe the output. So what output we need to observe, that we need to see. So let's see one by one. So the different observation this toolkit will provide, like is giving what is the probability or what is the amplitude of 1. If you're getting output as 1, what is its amplitude? Amplitude could vary. If it is a Fourier transformation, we getting amplitude lesser than 1 also. If it is a computational basis, then we get amplitude 0 or 1. Right. So this is showing just giving one picture, like what kind of evaluation we can do. This is state vector, and then is a quiz sphere also. In a quiz sphere, you can see a phase representation with different colors. So right now it is in a 1 state, right? So whatever circuit I have taken, so it's giving an output of giving a fixed output of 1. So if my target is I want always the output to be 1, so I can use this XOR or whatever circuit I have taken. So you need to observe this quiz sphere very minutely if you want to see the phase shift of your circuit. Like right now it's a blue color, it's represented as 1, so it's at phase 0. So if it will be a dark brown color, it will be like pi. It will be a pi phase. Likewise, there are other two ways. So computational basis will be either on 0, pi by 2, or 3 pi by 2. Whereas if you consider Fourier basis, it can be at any angle with not dark color. Right. So I mean, there are other gates also, poly gates, and their matrices. Hadamard gate is the popularly gate used. Just repeating the same point give us a superposition state, and there is a matrix. This is a matrix. We need to remember the Hadamard matrix: 1 by square root 2, 1, 1, 1 minus 1. And if you apply the Hadamard gate of 0 and 1, what it result to, it will give a superposition state of cut 0 plus cut 1 by square root 2, and for 1 it will give you cut 0 minus cut 1 by square root 2. So if you start dragging the Hadamard gate, so you can see a Hadamard gate. I've dragged one Hadamard gate. I have taken two channels, one a quantum channel, another one is a classical channel. On a quantum channel, I applied the Hadamard gate, and so the Hadamard gave us a superposition state, which state that there's a 50% probability we'll be getting cut 0 or cut 1, and or qubit 0 or qubit 1. So you can represent here probability. So left bottom side, you can see the probabilities. So their probability of both of the qubits. Qubit could be on a 0 state, it could be in a 1 state, right? So, and what is the probability? There's a 50% probability that it will be getting a 0 state or it will be getting a 1 state, right? So, and on the right hand side, you can see the Q sphere, and you can represent that there are 2 states possible. cut 0 and cut 1. Cut 0, both will be lying in a phase 0 in different orientation, but will be lying at a phase 0. So, and there is a code also given on right top side. So we know what is Hadamard gate. We know that it gives a superposition state, and we know that the probability of getting 0 and 1 in Hadamard gate will be 50%. And in this one, we have just checked it using Qiskit. We have dragged the Hadamard gate and we observed the graphs, and we found that it's working, right? So obviously, I mean, somebody who has done the Qiskit has done it, but for us is the learning. So this is a one Hadamard gate, and what change I made is right now there are 3 channels. There are 2 quantum channels and 1 classical channel is there. So 2 quantum with quantum channel, you can observe the difference in output. In previous one there was 2 channels, 1 quantum, 1 classical, but right now it is 2 quantum and 1 classical. So if you see Q0 and Q1, and since over Q0 only you have applied Hadamard gate, over Q1 you have not applied any gate. It will be an like identity matrix. So there is our identity matrix, a tensor product of identity with any of the gate will not result to any change. So it will be same output. So for the symmetry and for symmetry better representation, we write the identity matrix. I'll show you how we do that. But right now there are 3 channels, and over 1 channel Hadamard gate is there. And what change we have observed, since there are 2 qubits, input is of 2 qubits, so the possibility, there will be 4 possibilities: 0 0, cut 0 0, cut 0 1, cut 1 0, and cut 1 1. So the 4 quantum output possibilities are there. And if we apply like this, three channels with one as identity matrix, one as a Hadamard gate, another as a classical for measuring the output, will be getting output as either 0 0 or 0 1 only. So we need to understand, we need to apply this Hadamard gate mathematically with the inputs, with different set of input we are doing, and then we'll be able to understand why it is saying that it is giving 2 output only. Why not 1 0 and 1 1? Why it is giving 0 0 and 0 1 only? And if you see the orientation of 0 0 and 0 1, and it is on a phase 0, and it is I mean both will be lying in a different orientation, so at a phase of 90 difference. So this is what we need to observe, right? So we have seen that with single Hadamard gate over 2 channel, 1 classical, 1 quantum, how does this quisphere and the probability look like? And likewise over 3 channel with 2 qubits and 1 classical bit, how the difference like. So you likewise you can vary the Hadamard gates. So right now there are 3 classical channel, 2 Hadamard gates are there. So output difference in the probability will be like every state is possible. With 2 qubit input, there are 4 possible outcomes are there: 0 0 0 1, 1 0, 1 1. So there are chances that we'll be getting all of the outputs. So output could be anything, and with the probability of 25%. Each of the qubit probability will be 25%, and this we can see in the quisphere as well. So everyone is lying at phase 0, but with a different I mean lying at the phase 0 but at a different orientation, right? So I have given you a picture like how we can start practicing with the Qiskit. So that is just few examples, like before to be able to actually implement any of the algorithm, we need to do a lot of these practices. We need to observe the outcome of each of the gates, then we can better write the algorithms. This is my experience. So it could differ for you. Like let's start with the algorithms. The algorithm is Bastine-Vazirani algorithm, right? So what is our expectation from this algorithm? So I told you that if there are 2 persons, one is the challenger provider and another one is a challenger solver. A challenger provider has to put a challenge, and challenger solver has to solve this challenge. Now challenger solver can solve this challenge in one go or in multiple goes. So what the classical computing approaches says that in on a classical computer we need multiple tries. But on a quantum computing, this claim that we can guess any random number in just one go. How it is possible? This we need to see with an example, right? So if you see, I mean, if you're giving to a human being, what the human being will do, it will try to make every possible combination. Like you in your mind, you pick the random number as 1 1. But for a challenger, you told that there is a 2-bit number, 2-bit binary number, and you need to guess the number. So what the challenger solver will do, he will guess that the output, the random number could be 0 0 0 1 1 0 and 1 1. So he'll try every possible combination. In the worst case, it will be 4 possible combinations are required. In a classical way, if you want to solve the same problem on a classical computers, we can check each of the bits. And how we can check each of the bits? Let's see with an example. So this is one example here. Like I have taken an input of 1 0 1 1 0 0 1. So this is an input. And what I'll do is I'll make this length of this one is 7. So I'll make 7 vectors. First vector has 6 times most significant bit 0 and least significant bit as 1. Likewise, I will vary 1 for each of the vector. I'll be getting 7 vectors. And I'll apply the AND operation. So over a classical computers, at least 7 matching is required. So for a 7-bit number, 7-bit random number, I need at least 7 vector and an AND operation to find out the right random number. Right. So for n length, we need n vectors. So the computation complexity increases for a classical computer with the increase of length of the random number. But in case of quantum computers, we can do this with one shot with any length. So how it is possible? So we need to investigate this, and this can be done with Bernstein-Verizani algorithm. And what step I usually follow is first we'll take a fixed input. So we know that we need to make it for undefined length and for any period. In randomization algorithm, there is a concept of period also. So how frequently it is repeating, whether it's pseudo random or pure random number function, that we need to see. But what I start is I'll be fixing one number, and that number will be known to me, and to the challenger solver it will be known to me, and then I'll design the circuit. After designing a circuit, I try to reduce the number of gates. That's a verification process, whether I can apply some other circuit, whether I can make it more cost efficient. And once I'll be getting the desired output with some fixed set of circuits, then I'll be giving it for the final testing phase, right? So, and then aim is to modify this one for automated way for any random input and for unknown values. So what I automated is any random number with any random length input with unknown values. And then is to verify the circuit and test the circuit. Test the circuit is optional in case of automated. So let's see why it is optional in this one. So earlier we have used this one, Qiskit. Earlier we used the Qiskit in a drag and drop manner. So now we are using a Jupyter notebook to do the implementation of this algorithm. Now, a large number of examples are available on Qiskit help web page or the GitHub repository, right? So you can take help of them and you can implement those. So what I'm doing is here is I'm calling the Qiskit library and calling the visualization module, and then taking one variable in the second execution as secret number, and it's of 7 length, and it's 100 101. So then I need a circuit. So I need a circuit. So I need to execute an API quantum circuit. So quantum circuit with 8,7. So what is 8,7? So it's having an 8 input with 7 qubits. So since the length of the secret number is 7, so I need 7-bit input, but I need 8 quantum channels. And it will obviously add one classical channel. Is after measurement we need a classical channel. So outcome of the quantum gate will be in a classical channel only, will be a classical. And 8, 7, I have explained you. This is the requirement of the algorithm. We need to take 8 inputs, right? Because over the 7 inputs, we'll be applying the 7 input or 7 secret number that we have selected. Over 8, we'll doing some computations. Like you can see on the right hand side on Q0 to Q7. The Q7 is the 8th position. There we have applied the X gate and poly X gate and the Hadamard gate. So why X gate word first? Why Hadamard gate? This we can is the purpose of verification. So we will discuss this with an example and outcome also. And then you already know, I guess, that you have taken a variable circuit and you have applied the Hadamard circuit and you're providing a range 0 to 6. So you 0 to 6 Hadamard is applied over the quantum channel starting from 0 to 6. So Q0, Q1, Q2, and so on up to Q6, a Hadamard gate is applied. So H is Hadamard gate, then is circuit dot X and over 7. So Q7 over Q7, you have applied X gate, and then you have applied circuit dot H7. So Hadamard gate is applied after X gate, and then you put a barrier. So better representation, you put a barrier. So it has nothing to do with the computation. And then is circuit dot draw output dot MPL. So since you are using matplotlib visualization module, so you want output in a matplotlib with the random color circuit. So coloring is there, so everything we are drawing in a matplotlib. So this is one typical example how we can start with an algorithms. So right now we have not successful in the algorithms. We have selected the random number, we designed the circuit. So let's see what is the next one. So this circuit designing is not completed yet. In execution number 4, you can see we need to apply control NOT gate, right? So circuit.h, circuit.x, circuit.h7, all these are we have already done in the previous slide. We put the circuit barrier there, and thereafter we are applying the circuit CX, control X gate. So we are applying 3 control X gate, and where we are applying those control X gate over bit numbers 0, 2, and 6. Over a 7 qubit input, we are applying over 0, 2, and 6, and we are XORing it with Q7. So first, if I take first control X gate, that is circuit, this one, this is circuit 07. So Q0 and Q7 is there. So Q0 is this one, and it is XORed with Q7, right? So Q7 is the channel which we required in the algorithms to successfully implement this algorithm. So right, so there is a 2 and the 6 is there. Why we have selected 206 here? So if you see the previous slide and the number here, so this is the 0th bit, this is 1 bit, and this is 2 bit, and so on. This is the 6th bit, right? So those bits which are having 1, I told you in the beginning, we'll be taking a random number, and the random number will be known to the challenger, and challenger knows what is the bit value, and he will try to design the circuit. So he knowing that at 0, 2, and the 6th position, we are having 1, right? So that's why he's XORing it with 1. That's why he's XORing it at 1. So 0, 7, 2, 6, and 6, 7 is XORing it. After XORing it, put another barrier for this representation and output over a matplotlib. So you know that like over a quantum circuit, we put measurement to get a result over a classical channel. So here you can see this is the measurement. So all these measurement over every quantum bit channel is integrated with the classical channel. So get the classical output, right? So we are executing classical computers. We can understand our classical computers. So I mean in classical language. So that's why the classical channel is being taken. It's another way of explaining the same thing. So this is the complete circuit, right? So what we have done is you can see the this execution here. This one. We in previous we have seen that we applied XOR over 0 to 6. Only orientation is changed. Earlier it was 0 to 6, now it's 6 to 0. Hardly matters. operation same, we put the barrier and then put the Hadamard gate. So in between we put another Hadamard gates as well. So so we know that if you need identity bit, we need to apply Hadamard gate twice. So this property is usually checked when you are designing the circuit. Right, so then we are applying the measurement. So each of the over channel, quantum channel, measurement is put, and then your output. This is the circuit drawing, and then you can see we are calling the quantum simulator. Here we are calling the quantum simulator. There are different type of simulators we can call. List is available I've told you in the slide also, there was an architecture diagram, what kind of things you want to do. Accordingly, the simulators is available. So we're calling the chasm for this, and by backend is equal to simulator. By default, some simulator it will pick which one is available, and by default it will pick any of the quantum computers also. So we can specify a specific computer also. We'll see how to do that, and we are executing this with one shot. What we want is, over a quantum computer, in one shot we should be able to get the random number. So we are trying with one shot, and we're getting the printing the result. So you can see that with this circuit I'm able to get the desired output. So this was our random number. So this was our random number, and we, from the random number, we try to design a quantum circuit, and we design the quantum circuit also, and we get the desired output also. Now you can say that this input was prior known. So what is the big challenge? So at the first step, I usually start with this kind of approach, and thereafter we can automate the complete circuit. We can apply some Python concept to automate the same thing. We'll see how to do that. But you need to, before that, you need to see one more thing. So here the execution was with one shot, and here the execution is with 1024 shot. So you can take thousands of shots to verify your circuit. So here you are verified with one thing, and you have got the output also. This was the goal of the algorithm also. In one shot, quantum algorithm should be able to guess the random number. And if you're trying more than one shot, then also you're getting the same output. So all of the times you're getting the same output. So this is the testing thing. Is it the one shot only is giving the right or the desired output, or it is like every time we are getting the same? So we are getting every time the same result and the desired result. So we successfully designed one circuit for this, and we need to now see how to automate this. So let's see the automation. Automation means for any length, automation means for any length, for any number, we should be able to guess it. But before that is doing some sort of testing. I told you, like once you have successfully designed the circuit, what you can do is you can try to reduce the gates. So why you will try to reduce the gates? Because you want the circuit to be computational efficient, or your algorithm should be computational efficient. So is there any way we can minimize these gates? So this is just one try how you can do this. So what we have done is, if you can recall, our QCA’7 channel, we were first applying the X gate, and then thereafter we were applying the H gate. So we try to reduce one X gate here, and we try to see the output. So if you observe the output using this chasm in the same single shot, we try to get the output. You are with one shot, if you're trying, you're not getting the desired output. So that means with this reduction of the gate, will not be getting the desired output in single shot. But will I get the result in multiple shots? So I need to see in how many shots and with what probability I'll be getting the desired output. So I can see here, this output is coming 503 times, and this output, which is the desired output, is coming 521 times. So there is almost 50% probability that we'll be getting two outputs, and the desired output probability is little high, right? So but with multiplied times we are getting the output, but this algorithm or this circuit will not be successful for single shot. If we want single shot, we need to rethink of our circuit. So let's see how to automate, I guess now. Yeah. So this is an automation process. So this is an automation process. So this one is the previous one execution, previous code only. I put it here just to show the comparison, like what things we are going to modify. So this is the modif one and the desired one. So what we are doing is we are using the same secret number. Remember that the secret number value I have changed in this execution, doesn't matter. So what we are doing, we're going to use the length function just to compute the length, and then we are using the range function. So here also we were using the range, but we were specifying in a scale bracket. The other way is you can use the range function itself to do the range. I mean, because in an automated way, we do not know what length the user will input or what length the challenger provider will take. So that's why we are taking here the range. It will be an automated way. Whatever length you will take, it will automatically make the quantum channels and apply the Hadamard gates. And then you need to apply the X gate over last plus one channel. So over this channel, we need to apply this X gate before applying the Hadamard gate. So these two lines are giving us like circuit X length secret number. So since in Python, the indexing start from 0, so that is why we need not to add plus 1. We can do this with length secret number itself. So then is we put the barriers like we did in earlier case also. And then we are applying the control X gate. We need to apply the control NOT gate. Now in applying the control NOT gate, we need to check. We need to check what we need to check, which bit is 1. Over that bit only we need to apply this control NOT gate. So here we are just applying the for loop, and each index and the value for each index and value we are checking here. And if it is 1, if that particular bit is 1, then only we are applying the control NOT gate or X gate. Then we'll put a barrier. So all these are randomly put. So all these are randomly put as per the random input, right? So and then we'll put the barriers and then put the range over it. Since we need to apply the Hadamard gate here, over the Hadamard gate, we need to again apply this over the range of a length of a secret number. So that much Hadamard gate we need to apply. And then we put the barrier to do the measurements. So this is an outcome of this print statement. This print statement, we have added one print statement just to show you like what input we have taken. So we have taken an input of this 1 1 1 1 0 1 0 0 0 1. So this is the input we have taken. And if you run over the Quasm simulator, and we try to execute with one shot, are we getting the desired result? Yes, we are getting the desired result. So this was our aim. So we started with the aim that we need to design an algorithm where the challenger solver should be able to get the random number in one shot. And using quantum computers, we can do this. So you can see the power of quantum computers. So here in our classical computers, we have just discussed at the beginning that we need at least n number of vectors. N is the length of the binary bit or binary bit generator from a numeric bit given. So that much is minimum required. But here in the quantum computer, we can go in one shot. So if you integrate this with the quantum blockchain, so in a quantum blockchain, again, there are data mining approaches where the challenge generator, challenger verifier are there. So if somebody is able to get the challenger verification in one go, it is easy to break the quantum. It is easy to break the classical blockchain. So, I mean, the popular blockchain like your Bitcoin and the Ethereum, earlier they were using the proof of stake mechanism. Proof of work mechanism. So in proof of work, we need a challenger verifier has to solve the problem within 10 minutes, right? The multiple miners which are competing, and they will be getting maximum time of 10 minutes. And one who solved within the 10 minutes, he'll be the final person who will mine the transaction in the blockchain. He'll be getting the credit also. also. But if I mean the miner get the power of a quantum computer, everyone will be able to solve in a few seconds, few milliseconds. You know, the result of quantum bits is can be, will be getting output in few milliseconds. So that is just one example. If we integrate this algorithm with quantum, with the blockchain approach, how easy it is to break the blockchain. So we need to think of I mean, that's why the Bitcoin and Ethereum is move to the proof of stake mechanism. One of the reasons, right? So that is one observation, and here let me clear it. Right, so you can see this one output here. It's just one diagram with different input. It's just showing, I mean, we tried earlier with the 7-bit input, but this is a bigger length input with more number of ones, and the algorithm is successfully working and is giving a result in one shot. Right, so that is just an execution, another execution. This is how we test. Then is the second algorithm. So this is also an important algorithm called Dutch algorithm. So this is the first algorithm which proved that classical computer is, quantum computer is better than classical computers. So what this algorithm is, and what is its goal, how to achieve this goal, what are the mathematical computations. Let's quickly see this. So observe this. I told you what we do is, if we have one coin, we'll give some input, one coin or one function will give some input and we'll get some output. If input is equal to output, we'll call it as a constant function. And if input is different from the output, we'll call it non-constant or a balanced function. So output could be a constant or a balanced one. So in a classical approach, in a classical computer, if we need to do this, at least 2 tries are required. So you give a try for one flip, it could result to 0, another flip, it could result to 1. And if you try, first try could result to 1, other try could result to 0, or any other one is also possible. But at least for 2 set of things, minimum of 2 tries are required. But quantum computers claims that we can do this with 1 try. So how we can do this with 1 try? So is it possible with thousands of shots? So that we need to see in implementation. But before implementation, we need to see some of the mathematical concepts also. Like this is the circuit which is used in Dutch algorithm. So in Dutch algorithm, there are input set of register, there are output register, and we're getting some output, and there is a black box. U function is there, and for a Dutch algorithms, if you go to QCA’ help web page, you will be finding different UF functions. There are different possibility of UF functions is there. How it is doing the computation? So you are passing 2 qubits, cut x, cut y. So passing a cut x and cut y here, cut x, cut y, and you are applying the UF function. So output is cut x will be cut x only. So it is, this is the same cut x only, whereas cut y will be y XOR fx. So y is this one. So this y will become this y and XOR of fx. So fx is here, it is x, so it is fx. So this is the when you applied it. So when you do reapply the same thing, you know, quantum circuits are reversible circuit. That means if you apply the same circuit twice, you'll be getting the result back, right? So we were just testing whether this UF function with these kind of outputs is giving is reversible or not. So if you apply UF here and X is applied here, and this one is like this become X and this become Y now. When you are applying for this, you have second time, this become X and this become Y, right? So X become X again here. Over this, you are applying this and you will be getting this, right? So this is Y. So Y is written Y plus Fx XOR Fx. XOR Fx we have to write according to this formula, right? So this XOR Fx, XOR Fx will be cancelled out, it result to 0, and anything XOR with 0 we know is the same thing. So we got X. So cut X, cut Y, we are getting here. So right, so we have seen some of the computations for the circuit that Dutch algorithm uses. And next is there are different approaches we can do with Dutch algorithm. Some are right approaches, some are wrong approaches. I'm trying to explain this with a wrong approach. Like if the output is dicey, so there are 50% probability that we'll be able to identify whether the desired circuit is a constant circuit or a balanced circuit. So what we want is, we want, if some circuit is given to us, we should get whether the circuit is constant or balanced one in one shot, right? But if you're giving a dicey output, then that is not a right approach. So what wrong we are doing here is we are trying different type of bases. So we are trying plus cut and zero cut, right? So different type of bases are there. I told you there are computational bases, there are Fourier bases are there. Fourier bases are inclined to an angle, whereas computational bases considered as 0, pi by 2 and 3 pi by 2, right? So over that. So if you see this circuit, so we are applying this circuit and we're trying to get the outcome as a single outcome. So here we apply the UF functions, cut plus XOR cut Y. So what we have to do is, we are applying here Hadamard gate, and Hadamard gives a superposition state. So this is the superposition state. So so plus is going over this channel. So plus over plus only will be getting the Hadamard gate. We'll be applying the Hadamard gate. So we applied the Hadamard gate here, and 0 we are keeping it as it is. So 0 is kept here as it is. And then we are opening the brackets. You can write this way also, UF0, and this 0 is multiplied with this, and this come from this, and the result to this one. So like that way you can write for this 1 also, and 0 also, and UF is coming from this place. So 1 by square root 2 is coming from this. And if you see this one, 0 XOR 0. So we can write this one as F0. We are writing this as F0 because UF is also a function, FF is also a function. We're just saying that two functions are equivalent. So writing this way. So this ultimately result to a 0, something multiplied by 0, 0 F0, and resulting to 1 F1. So it's giving a dicey output. So it's not giving a fixed output. It's saying that the probability of getting two different output is equally likely. So there'll be slight variation in the probabilities, but they are equally likely. So this is not what we want. We want an exact output. So we need to see what computation we can do. So here, we're trying with a right approach. We're trying to do with the right approach. So in the right approach, what we're doing is we're using Fourier transformation. So either we go completely with the computational basis for testing, or we do for the Fourier transformation, Fourier basis for the verification or testing. So here we are going with the Fourier basis. So anyway, if you pass as a computation basis also, then also after Hadamard we are going to take these things also. I hope you can understand there's no difference. So we are going to apply something different. We are applying Hadamard gate, XOR gate, and Hadamard gate like we did in the previous algorithm also. So what we're doing is we're doing some kind of multiplication here. So with plus operator, we pass the Hadamard gate. So we applied the Hadamard gate here. For negative also, Hadamard is there, square root into square root become 2. So that is showing the final result. So at different stages, different output stages, Chi1, Chi2, Chi3. We're doing some sort of computations, and we are finding the results. Right, so I'll keep on going like this. So only 5 minutes are left. So so some other time I'll be
अच्छा आदर्श
covering. Right, yes ma'am.
आदर्श हाँ इसमें ये बताओ कि अगर मान लो हम सपोज वी आर गेटिंग द इक्वल नंबर ऑफ जीरोस और आइदर जीरोस और वन देन वी आर कंसिडरिंग दिस एज ए बैलेंस्ड वन.
Right ma'am.
तो ये जो इक्वेशन जो हमने इतनी सारी की तो वी विल नेवर गेट द बैलेंस्ड वन.
No, we'll be
Either-
getting a balanced one. We'll be getting a balanced one.
अच्छा
Will be
मिलेगी.
like there is a complete derivation. There is a complete derivation. So I will not be able to explain this thing in next 5 minutes. So there is a complete derivation of it. So you
अच्छा,
can see the outcome of this
Okay.
derivation. So if you're passing the plus cut as an input over header mode, it will result to 0. So I was about to prove this using Qiskit also. So I have to show this one also. Like if you apply header mode gate twice and then measure it, we'll be getting always 0. So if you integrate with the XOR function, we'll be getting 1. So in which case it will be getting 0, in which case it will be getting 1, how to automate this. So we need to understand this in detail, but mathematics is also required to understand this. So, but we'll be getting a definite input. That's I've seen it and it's working.
Okay, thank you.
Any queries from the participants? Any queries? Yes, please, you can write your queries in the chat box. Oh, thank you, Adarsh. It was really a very enriching session, right? It seems you have done a lot of work in the field, right?
Right. Thank you, ma'am. Thanks to you.
You have, yeah.
Very few people are working in this area.
अच्छा एक और बात बताओ आदर्श.
जी मैम.
हाँ इसमें ब्लॉकचेन के क्या इसके प्रोस्पेक्ट्स हैं इसके अगर मान लो हम क्वांटम कंप्यूटिंग ब्लॉकचेन में लगाएं.
अभी तो मैम ब्लॉकचेन में मैंने एक ही आर्टिकल देखा जो MDPI में है, और एक अभी स्प्रिंगर में मैंने देखा कल आर्टिकल जो ब्लॉकचेन पे आया. वो कम्प्लीटली थ्योरेटिकल है. उस पे ऊपर जैसे फिजिक्स पीपल यूजली एक कंप्यूटेशन बेसिस के ऊपर इक्वेशंस लिखते हैं, उनके ऊपर वो लिखा हुआ है. तो बट फॉर एवरीथिंग लाइक क्वांटम स्टोरेज, how to store the quantum bits, because quantum bits light for a very small time, how to store it for a long time, how to transmit it for a longer distance with multiple intermediate devices. There are a lot of challenges are there, but there are devices available, there are concepts available, how to store it in a blockchain, how to integrate in a blockchain network. तो जैसे हम ब्लॉकचेन नेटवर्क बनाते हैं, ट्रांजैक्शन दिखाते हैं, उसमें माइनिंग प्रोसेस, स्मार्ट कॉन्ट्रैक्ट बनाते हैं, तो ऑल हाउ वी कैन डू विद क्वांटम बिट्स, व्हाट काइंड ऑफ क्वांटम सर्किट्स आर रिक्वायर्ड फॉर अ स्मार्ट कॉन्ट्रैक्ट. सो इसमें देयर आर वाइड अपॉर्चुनिटीज व्हाट वी कैन डू.
अच्छा ओके. Any queries? Participants, any queries?
I think there are no queries. Thank you, Adarsh, for such a wonderful session, and a lot of you still have lot many things to explain, and you know all the algorithms, explaining all the algorithms in details and so precisely. So the participants must have gained, right? So thank you so much for being here.
Thank you, ma'am.
For sparing your valuable time. And,
Thank you, everyone. Thanks,
time.
everyone, for your patience and for listening to me. Thanks, everyone, to organizing for this wonderful event and inviting me, ma'am, once again.
अच्छा था
Thank you,
आदर्श.
everyone.
ओके बाय. बाय
Bye.
आदर्श.
Bye. So with this session, this is the end of the day. So we will join tomorrow again at 10 a.m. for the last day, last two sessions and the validate. Thank you so much.